Problem 5, Week 3 homework. So in this problem, you have a mass of an unknown weight hanging from a wire rope that's taken on this, what we might call a catenary, or perhaps a better term would be a funicular shape, which just simply, those are both Latin words. Catenary means chain and funicular means rope. It's the shape that a tensile member takes if you anchor it on the two ends and then apply a weight to it in the middle. And what we know is that the tensile strength of the wire rope is 100 pounds. And the question becomes, what weight is the maximum weight that this string can support with that tensile strength? So if you think about the weight of the object, well, the weight, there has to be a vertical reaction. If we think about just basic fundamental static equilibrium, right? The sum of the forces in the y direction must equal 0. So if you think about these two wire ropes, we could think about them independently. Each is going to exert this upward force, which I will call O. And so if you think about the weight of the object has to equal the opposite side of one triangle plus the opposite side of the other triangle. Or another way to think of it is the weight of the object is equal to 2 times this length when we get that length proportional to a force. Okay, so those are just relationships we can take from it. Now, you'll notice that this triangle is drawn in distances, and it's referring to the geometry of the wire rope. But here's the interesting thing that happens with purely tensile members like wire rope is that essentially the positions that the wire rope ends up taking represent the vectors. In other words, the wire rope can basically only pull axially, and so it kind of points the way, which means that if we can solve the geometry, then we can just simply scale this so that it relates forces rather than distances. So some basic assumptions we need to make. Vector O acts purely vertically. There is a corresponding leftward vector that's created by this wire rope. I'll call that vector A. It acts purely horizontally, and the actual tension in the wire rope is related by A squared plus O squared equals T squared, which is just Pythagorean theorem. I've just substituted an O for B to better reflect what part of the triangle we're talking about, and I've substituted a T for C to reflect the fact that we're interested in finding tension. Well, let's plug in what we know. We know that A is 10.5. And 10.5 squared plus O squared equals 12 squared. And now we can do some turning of the crank. We want to get O by itself, so I'm going to leave O on the left side. O squared equals, and I'm going to subtract from the right side this quantity, but first I want to simplify the 12 squared. Well, 12 squared is 144, and it's going to be subtracted from that is going to be 10.5 squared. Let's find out what 10.5 squared is. Okay, 110 and 1/4. Now, we aren't interested in O squared, we're interested in O, so we're going to take the square root of both sides of the formula, and on the left side that's going to give O. On the right side, first we'll take the subtraction inside the root symbol, and then we will take the root of the difference between these two numbers. So I'm raising it to the 1/2 power, which is equivalent to taking the square root again. And what we find is that O is equivalent to about 5.809. And if you think about all of these numbers that we're working on, these are all distances. So this is inches. Now, here's where we can make a little leap from geometry to force, is that we know that the length, we can think of the length of this 12-inch vector as representing the 100-pound force that we're trying to develop in the wire rope. So 12 inches is to 100 pounds, as 5.89 inches is to some other number of pounds. Over, we don't know how many pounds. So essentially we're just scaling this length of this vector by the ratio or the proportion that relates 12 pounds and 12 inches and 100 pounds. Well, let's do some cross multiplying. So you get 12 times whatever the number of pounds is equals 100. We're going to move the decimal point 2 places. 580.9, and in both cases the units are actually inch pounds because we're multiplying inches by pounds. So now to get the question mark by itself, we divide both sides by 12 and we get 580.9 over 12, and that is going to equal the force developed by vector O. So it's going to be some number of pounds. So 580.9 divided by 12 works out to about 48.4 pounds. Now, what you have to remember is that the weight of the object is actually twice the value of O, and that's because this wire rope over here also has some upward thrust. So that the total weight equals 2 times 48.4, which equals 96.8 pounds. And again, the lesson to take from this is that wire ropes have to express loads, have to carry loads axially, which means that the shape that the wire rope takes, or the direction that the wire rope is oriented in, represents the orientation of the vector that would represent it. And when we get scenarios like this where we can get specific angles and specific ratios, we're able to convert from geometry to force if we're able to develop some type of a ratio of distances to forces, which we did here with this proportion.